All right. We'll finish electrostatics today, at least the algebra-based parts, by discussing charging and how electric fields interact with matter. So, the most straightforward method of charging is charging by friction, where if two objects are rubbed together, you get a transfer of charge. And due to conservation of charge, each object will finish with equal and opposite charges, because all the electrons that are transferred from one object go to the other, so it's an equal exchange. And we won't ever have to determine what object becomes positive or negatively charged, because that's determined by material properties of the two interacting. And there is a table known as the triboelectric series that would give that. So, for example, things like silk tend to become positively charged, and things like rubber tend to be negatively charged. So, it'll always be given sort of like this context. So, suppose that after a glass rod is rubbed with fur, the rod gains a net charge of 640 nanocoulombs. So we have a rod, and it was rubbed with fur. So this is a classic electrostatic setup where you have some rods and some fur. And based on charge conservation, we do know that the fur will obtain an equal charge, just of the opposite sign. And we want to indicate the direction of electron transfer here. Well, we know it's the electrons that are actually moving, because the protons are stuck in that nucleus. So the only way the glass rod could have become positive is if it gifted electrons to the fur. So we know that the rod gave electrons to the fur. And now if we wanted to calculate the number of electrons transferred during this process, we can just use the fact that the electron charge is known. It is a constant in our reference information, where each electron is worth 1.6 times 10 to the minus 19th coulombs of charge. So we have 640 nanocoulombs, so 640 times 10 to the minus 9th coulombs. And we just need to figure out how many copies of 1.6 times 10 to the minus 19th we can fit in there. So doing that, we can just do some quick division, and we know that we do expect a whole number here. We would get 4 times 10 to the 12th electrons. Because charge is quantized, so we know we can't get decimal values here. Even if we don't touch an object to another one, we can still get some electric forces and a sort of interaction, even without charge being transferred, given this effect known as induced charges or polarization. So if you bring an object near another one, a charged object will exert a force on the charge carriers such that they move to a more preferred state. And of course, it is the electrons that are moving each time, but we'll always model it using something like the picture above. So if I have a positively charged rod, you can almost think of it as sort of summoning electrons from the sphere towards one end of it. And if the rod was negative, it would sort of be scaring the electrons to one side. So the net effect of that is one side of the sphere becomes more negatively charged than the other. But it should be noted that since the rod did not touch the sphere, I know that there is no net charge on the sphere. But there will be a force. So people know the attraction rules where positive and negative attract and positive repel, but positive and neutral are also attracted, and negative and neutral are also attracted due to the phenomenon of polarization. Because these negative charge carriers will be attracted to the rod like this. So there will be a net attractive force, because even though there might be equal charges over here, that is a greater distance away, so the net force is going to be attractive still. So this is true in every scenario with polarization, that you do get a net attractive force. And it would be equal and opposite via Newton's third law. So here's a classic demo that's really easy to do. A balloon is initially not attracted to a neutral insulating wall. We then rub the balloon on someone's hair, and it sticks to the wall after gaining negative charge. We want to describe why this happens using charge distributions. So we're given that a negatively charged balloon sticks to the wall where it usually didn't. So, of course, this is about polarization. So we can just use the fact that this negatively charged balloon is sort of scaring the electrons deeper and deeper into the wall. So even though there won't be a charge transfer due to this being an insulator, we're still going to get a polarized model of the wall where there'd be more positives on one end of the wall than the other. What's really happening is a small number of electrons are getting moved deeper into the wall, giving this sort of net effect of the wall being more positively charged near the balloon. And since we have an attractive force closer than the repulsion force, we know that the net force on the balloon will be attractive. The wall is also equally attracted to the balloon, but the wall is very big, so we obviously aren't moving the wall. So that's our explanation there. Charge is polarized. The wall is not charged, because if I count my charge pairs, I have 0, 0, 0, 0, 0 net charge. But there is still a force, because the charges that are attracted are closer to the charges that are repelled. So it is important to know that. Here's a common misconception question. An insulating sphere hangs from rest. It is unknown what sign of charge, if any, is on this sphere. So suppose a negatively charged rod is brought near the sphere and we have attraction. And upon seeing this attraction, a student might claim, well, I just saw that object get attracted to a negative rod, so it must be positively charged. So this actually uses polarization. So it is actually like a reasonable thought to think that, well, if I just saw this getting attracted to a negative object, it must be positively charged. But of course, we've neglected the fact that neutral objects are also attracted. Because we know that the positive case works, but also realize that if we had a neutral sphere and brought a negatively charged rod near it, we would get polarization, because we would get positives that move towards one end of the sphere, and we'd get negatives that move towards the other. Of course, it is the negatives that are actually moving every time, so the rod is sort of scaring the electrons away, but we would get a net attractive force even from a neutral sphere. So that means we just need to do an experiment to rule out the neutral case. So that is anything that could definitively say whether the sphere is neutral or not. So we probably need a positive rod for that. So if you bring a positively charged rod near the sphere, that's enough to figure it out. Because first of all, the easiest case is there's no way to get repulsion if you're uncharged. So if you get repulsion, you instantly know what sign the charge is. But if you bring the rod and it's still attracted, so it's attracted to both a positive and a negatively charged rod, well, that's actually how you prove it would be electrically neutral. Because if you repeat the rod experiment with a positive one, we see that this time the electrons are being summoned to the right end, so it's still going to be an attractive force. So we still get the sphere being attracted to the rod. So kind of tricky there, so just remember that neutral is attracted to both. Here's an interesting way of actually getting a charge without actually touching a charged object. So this is called charging by induction, and I call this my IKEA instructions because I didn't put any text instructions here. So we have two neutral spheres, and then I bring a negatively charged rod near the spheres. So this is, of course, an exaggeration, but the negatively charged rod is going to scare away the electrons so that more of them are in the rightward sphere. So then, if I separate the spheres while the negative rod is still in the picture, I get two spheres with opposite charges, and I didn't actually touch them to the rod. So it should be important that, like, this rod has to still be here, because if you move the spheres away after you've sort of removed this rod, you still, you'd get electrically neutral, but it's sort of implied that I didn't remove the rod yet. So this is charging by induction. This is the example. Another thing we can do is we can ground something. So if you connect something to ground, which is the ground, or earth in most cases, you can imagine the ground as being a source or sink of electrons. So the electrons would always like to go somewhere, but they can't because they're trapped to an object. So in this case, when you ground something, the charge carriers are free to move wherever they would like in response to the forces around them. So our grounding symbol is very similar to the battery symbol. It just has 3 parallel lines. So first, let's talk about what happens if we just ground 2 objects by themselves. So first of all, we see that there's a net positive charge on the first sphere. So the positive charges are not very happy that all the positives are crammed together in that sphere, so they would really like to leave. So in order for the positive charges to leave the sphere, they could travel into the ground, but we know that's not actually what happens because the positives aren't the ones moving. So in order to neutralize the positive charge, electrons enter from the ground to correct that charge imbalance. And then conversely, all the negatives in this sphere don't want to be together. They would really like an outlet to leave. So as soon as you give the electrons a free path to the ground, they're of course going to leave the sphere and enter the ground. So the charge is neutralized that way. So notice that in both cases, it was electrons that are moving. So the ground could either provide electrons if you are positively charged and need to be neutralized, or it could serve as a sink for electrons and remove excess electrons from your system. So here's a common thought experiment type problem where we look at signs of charges with and without grounding. So we have a negatively charged sphere and a neutral sphere initially. They're both conducting. So in the first scenario, we bring the negatively charged sphere close to the neutral sphere, and there's nothing connected to either sphere. But in the second case, the second sphere is grounded. So it's definitely easier to examine this first case. We're going to be interested. The question is asking what the charge is on both spheres, the sign in each case. So we could actually answer the sign of the charge on the right sphere in scenario 1 instantly because nothing ends up touching the sphere. Because unless if something is entering this box to take or remove charge, the charge must remain constant. So this is just an example of polarization because the electrons would get scared deeper into the sphere in this case. So we actually do get attraction. So just because there's no net charge, don't think there's no attraction. So the spheres are attracted to one another, but there is no net charge on that second sphere. But in scenario 2, think about what happens. So let's consider like this case from the first problem, where it's polarized. Well, if you give this sphere a ground outlet, what that does is that allows the electrons to not just polarize, but the electrons get to go where they would like, and that is away from the other electrons in the leftward sphere. So that means that the electrons totally get scared into the ground, so we get a net positive charge on the sphere. So this is, again, one way that we can actually change the charge on an object because we connected it to something else. So in scenario 1, the right sphere becomes neutral, and in scenario 2, the right sphere becomes positively charged. Because in the first case, well, there's nowhere for the charge to go, right? There's nothing entering this box. But in the second case, the ground allows the electrons that would like to escape, it gives them an actual path. And obviously the left sphere is negative both times, because where would the charge go? So now suppose we can move the grounding wire, move the spheres, do anything we want. We're going to look at modified ways to get the spheres to end with each of the following results. First case wants us to just get both spheres to end with no net charge. Well, if we wanted to end the scenario with no net charge, maybe let's start from this case because this is what we know is kind of happening at the start. If I want both spheres to become uncharged, I should just ground one or both spheres. It's really the left sphere that needs to be grounded because the right sphere is already neutral. So all I need to do is just slap a grounding wire on the negatively charged sphere, because then all of those extra electrons that are crammed in the sphere and wouldn't like to be together can have an outlet to escape into the ground. So we ground the left sphere. And just for completeness, I decided to ground the right sphere too. But it's really only the left one that needed it because I need to dump its net negative charge somewhere. Then in scenario 2, our part 2, we want to make the left sphere positive and the right sphere negative. So we want the opposite of this. And of course, I know our clever people out there just saying, just take scenario 2 and change the order of the spheres. We can think of something a little more deep than that. So you can think about it for a second, but the key to this is going to involve charging the second sphere before you ground. So if we want charges to transfer, we just need to touch the spheres together. So if we touched these two spheres together, they would share the negative charge on the system originally, and then if you grounded the left sphere, it would dump off some of that negative charge into the ground and become positive due to the other negative sphere. So we get this case. Touch both spheres together, because then they'd both share negative charge, and then ground the left sphere, because that would cause the electrons to get pushed into the ground from that left sphere, so we get opposite charges. Of course, we could do the simple case of just flip the spheres around, but this is more creative. Now we're going to talk about conductors. This is a very deep topic, and there's a lot going on with this. So we said that charges would really like to move apart if given that possibility. And conductors are defined as materials where this sort of want to move apart can actually happen. So if I have given 3 positive charges to the center of a conducting sphere, we're trying to verify this rule that it says all charge on a conductor must reside on the surface, which means you can't have charge inside a conductor, you can only have charge on the surfaces. So let's say that a divine entity has granted these 3 positive charges to the center of a sphere that is conducting. Well, we know that based on Coulomb's law, we actually did this problem. The forces on these charges are going to look like this. But it's not just the forces that we can look at, because this is a conductor. So all these positive charges would get pushed that way, and they can actually move that way because it's a conductor. So this positive charge ends up here on the surface, this positive charge ends up here on the surface, and this positive charge ends up here. So we can see that, as expected, our positive charges will end up on the surface. So notice that there is no charge inside. And that is the conductor property we tried to prove. And you can repeat this with any number of charges you would like. It's going to do the same thing. They're going to try to maximize their distance from one another, and they're going to spread out along the surface. So that's our property. They move to the surface to maintain this maximum separation. They'd really love to get off the sphere from each other, but they can't, so they'll settle for the best they can, which is get as far apart as possible. So now let's see what would happen if the sphere was insulating. Well, this part would be the same, at least the forces would be. But the difference is, even though they're getting pushed, they can't go anywhere because they're locked in place due to the insulator. So the charges cannot freely move, so you basically are going to get just the same scenario as we started with. The charges would really like to move apart, but they can't. So when we talk about charge density, only insulators can have the charge density rho, which is that volume charge. Conductors are described by their sigma, their area charge, because it's a surface area. Now for our E field. This is the big E field property I'd like to convince you of. And that is that the electric field inside any conductor is zero during equilibrium conditions. And by equilibrium conditions, we mean as soon as charge is transferred, the charge will distribute to make this happen. It's on the order of 10 to the minus 10 seconds or something very small like that. The only time you would get an E field of not zero is when you're not in equilibrium, because you're forced not into equilibrium by like a battery or something. So in electrostatics, the E field is always zero inside a conductor. You can stop there. Like, you don't have to ask additional questions about it. If you know it's in equilibrium, you know E is zero, meaning the charges have stopped moving. So we'll try to prove this fact. But some consequences of this is that even if you're putting fields in the conductor from outside, even if there's charges deeper within the conductor, the field inside the walls of the conductor is zero. Charges will rearrange themselves to ensure this is true. And this does actually kind of work in an insulator too, but the field doesn't totally cancel out. So here's an example of what might happen. So let's say that I apply an E field, E1, to a conducting block. Well, what's going to happen here is, by definition, the E field gives the direction that positive charge carriers would move. So maybe I got some pluses, and I have some minuses just kind of hanging out in the conductor. Well, if it is a conductor, these charges are free to move. So what that's going to do is it's going to shove all of the positive charges to one end and all of the negative charges to the other. So we see that we'd get a positively charged end and a negatively charged end. And as a result, you would get another E field that exists, this one inside the conductor. Because again, based on our source and sink rule, we see that there would be an electric field pointing the opposite way, which we call a back electric field. And then we can see, based on vector addition, that these E fields are going to cancel out, resulting in zero net E field. And why it's exactly equal is because if it wasn't, there would still be forces on charges, so the charges would still be moving, so the E field inside the conductor is still building, so it's still canceling. So if the E field wasn't zero, then you wouldn't be in equilibrium yet. So you got to wait a little longer, basically. So where this argument breaks down for insulators is this step where the charges get fully separated. That doesn't happen in an insulator. So instead, you get these little baby dipoles where you get smaller back EMFs. You get smaller back E fields that attempt to cancel out the external electric field, but doesn't totally work. We'll return to this picture again with capacitors, because this is actually really important to how we can insert insulators into capacitor plates to increase their capacitance. It uses this idea. So insulators, some classes of them that do this can be called dielectric materials because they reduce the electric field. And a way you can look at that is literally like dielectric, because that is what the material is trying to do. It's trying to kill the electric field. So maybe conductors should be called kill electrics because it actually kills the electric field entirely. Alrighty. A positive charge is placed near a hollow conducting shell. So here is where we are going to become expert pattern recognition problem solvers. If I see the word conducting whatever, I am going to write two things on that. We only know one of them right now. I am going to write E equals 0, any region that is conducting. So in this case, that only is going to encompass this, because this is the only metal, because we're given that this is a spherical shell. So since it's a spherical shell, there's sort of this hollow cavity that exists inside. The E field isn't necessarily zero in there. We'll come back to that one. So what we know for sure is that since B and D are inside the walls of a conductor, we know that the E field is zero at points B and D. And now we'll look at case C. So there's something known as electrostatic shielding that says that if you're inside a conductor, you're free from outside influences. So this conductor makes point C ignorant of anything that's outside the cavity. So a common example of this is a lightning strike. So if this represents your car, if your car is struck by lightning, Your car will definitely feel the lightning strike, but you won't because you're protected. You are ignorant of anything happening outside the conductor. But if you put a giant Van de Graaff generator in your car, you will get shocked by it. So maybe if there's charges in here, I could have an E field, but it is a shield. So point C is gleefully ignorant to any charges that exist outside it because it is protected or shielded by the shell. So this actually guarantees that we have an electric field equal to 0, sort of tying at B, C, and D. So if we attempted to draw like an E field diagram, we would know it would look something like this, because it points away from positive charges. And we'll learn more specific rules for this in a little bit. But we know that it's going to look something like this, because we know that the positive is going to be a source of field lines. Maybe the shape's not totally accurate, but we do know that it's going to be something like that. But the important thing is that notice there is an E field at points A and E. Because if I place a positive charge at A, it will definitely get pushed away. And if I put a positive charge at E, it will get pushed away because it's repelled. And since A is closer to the charge than E, we know A has a stronger E field. So for our ranking, we know that B, C, and D tie because there's 0 E field. And then A is closer to the charge, so it has a higher E field at that location. So again, it should be noted that E equals 0 inside a conductor is basically what's ensuring that. So here's our ranking. It's 0 inside the walls of the conductor, so that makes B and D 0. But C is 0 for a slightly different reason. C is 0 because it's shielded from external fields. So there's nothing inside that cavity, so there's no way the field could not be 0. And the field is not 0 at A and E because they're outside the conductor, and E just feels the electric field less because it's farther away. So that's why we get our ranking. Now we have our other electrostatics term. We have potential. So we said earlier that delta V was equal to ED because the electric field points downhill to lower potentials. So if the E field is pointing towards lower potentials, but every point on your conductor has 0 E field, well, that means nothing in the conductor is downhill relative to anything else. So you actually get 0 delta V inside a conductor. Notice that is not 0 potential, but it's 0 potential difference. So what this means is that the entirety of a conductor is an equipotential surface, meaning the electric potential is constant. And it's usually a non-zero constant. So if there's positive charges around it, the potential is probably positive and constant. And if there's negatives nearby, it's probably negative and constant as a consequence of our V equals 0 at infinity assumption. And since a conductor is an equipotential, this must mean the quickest way to decrease your potential is to leave the conductor. So that means the E field is perpendicular to the conductor's surface. And another consequence of this is that the electric field at the surface of a conductor is not constant. So you do get an E field at the surface, just not inside. So charge accumulates more densely at sharp points. And I use this analogy of like a hallway, where if you have a wide hallway for people to exit, maybe like a movie theater or something, if you have a wide hallway, people might be able to just go across, like 3 across that way. But if you have a very thin hallway, the charges are more densely packed. And if the charges are more densely packed and there's sort of only one way for them to go, that's going to increase the electric field strength because these people are pushing each other harder. They're trying to get out of the movie theater. So the E field is stronger where the conductor is more sharply curved. So here's our little conductor fact sheet. E equals 0 inside any conductor, and V is constant at all points. All parts of a conductor are an equipotential surface, so the E field is perpendicular, and the E field is stronger where the curve is more sharp or has a smaller radius. Both of those are the same. So here's our previous scenario again. And I said there's two things we should write on any conductor. Anytime you see something is conducting, you should write two things in the conducting region. E equals 0, and not V equals 0, but potential V is constant. And we also visualized potential with color all the way back to circuits. So what that would mean, if I had a potential color coding diagram, everything in the sphere and on the surface would be the same potential color, which is why E equals 0. So you might actually start with V equals constant as your fact and say, well, everybody's at the same potential, so there's no E field because there's no downhill. Everybody's at the same height. So now we can go ahead and rank the potential at each of these points. So what we can first gain from this is that regardless of what's going on outside, we know that B, C, and D tie because they're all on a conductor or in it. And same thing, that C is in this cavity, so it's shielded from outside effects. So unless if there's something going on in the cavity at point C that could be affecting the potential, that could be contributing extra, it doesn't know anything about the outside world. So it's shielded. So B, C, and D tie for similar reasons as before, although it's not 0. So now we just have to figure out how it compares again. But we did say from earlier that the electric field, which is going to look like this because we know it's perpendicular to the surface of a conductor, and it generally is going to look like this because we know the positive charge is a source. So we said that electric potential is lower where the E field is pointing. Or another way of saying that is E points downhill. Not a very good end. Downhill. So what that means is that wherever the E field is pointing is the lower potential direction. So I know that this would be high potential because that's my positive charge or my hill, and this would be low potential. Since that's where the arrows are pointing. Another way of looking at this is using our terrain model. So this positive charge right here is creating a hill, and that's it. There are no valleys, so this just means that there is a giant hill over here, and then it's going to slowly flatten out and level out towards 0 far away. So we have a big hill, so A is going to be the highest height, and then we have a flat plateau throughout the entire conductor, and then it slowly decays back down to sea level. So either way, we get this potential ranking where E is the lowest potential because it is downhill. Then we have B, C, and D because they're slightly uphill. And then A is the highest, or it's the closest to the hill. So that's our ranking. So electric field is 0 inside any conductor, which means the electric potential is constant. So E being 0 is what demands the V can't change in a conductor. So all points on the surface have the same potential, which makes our three-way tie. And then we know the potential is higher at point A than point E because the electric field is pointing in E's direction, so E is lower potential. So generally, our potential is just decreasing from left to right. And if we were to actually graph it, because this might be a good visualization for us, if we were to actually graph it, we know that somewhere like near our positive charge, it's going to be an infinite spike. But then I'm decreasing in my hill, but then as soon as I enter the conductor, it's going to be a little plateau. And then when I exit my conductor, it's going to decrease towards 0. So this would be my potential graph, basically. So we get this plateau region inside the conductor. So now we have a fun little LaTeX diagram that I went through many tweaks for in getting this to code properly. We have my little shark fin or my saddle diagram, where this irregularly shaped conductor has a net negative charge, and it's conducting, so, well, it's conducting. I should have done that first. Conductor. What do we do whenever we see a conductor? We say E is 0 inside, and V is constant. Breaking my own rules by not saying that instantly. So that actually does instantly tell me the E field is 0 at D. So we are interested in ranking both the electric potential at each point and the E field magnitude. Well, first of all, marking up my picture just solved my first ranking because we said potential is constant through any conductor. So all of these points would be the same color, which means that A, B, C, and D tie. Because if the E field's 0 inside the conductor, there's no downhill direction. Everybody's at the same height on the conductor. Then we can do the E field. So the E field uses this curvature idea. So we said that the E field is stronger at your sharper points. Again, think like your lightning rods, right? You got to use that excess copper to craft something, I guess. So if you make your nice little pointy rod, well, the pointy part is going to have a stronger E field if that was attached to a conductor. So first of all, we know D is 0. The E field at D is 0 because it's inside the conductor. And then if I were looking at my curving, we see that A is the sharpest, B is slightly more flat, and C is the flattest. So just qualitatively, we could reason that, but how you technically do it, if you really were interested in that, is you could attempt to draw a circle tangent to the conductor at each point, and you could rank this sort of radius of each of these circles to how to actually definitively say that A would be the most sharply curved. So then so it's 0 at point D because it's inside. So I might write a little note down here that D is inside. So E is 0. And then we just do our ranking because C is the least sharp of the curve, then B, then A. So justify our rankings. Electric potential is constant, and that means the electric field is 0 inside, and it's strongest on the parts of the surface that are more sharply curved, also known as more pointy. Yes, that is a totally valid argument, is just saying A is the pointiest. Everybody knows what you mean if you say that. One might do a problem where we actually consider proving this fact. So this does come from the potential. So your quick like TLDR on why this is true and how we can prove it involves charge density. So since the electric potential decreases with radius, we know that where there's more radius, there needs to be more charge. But also surface charge density is proportional to r squared, so we see the r squared actually ends up winning. So the E field is inversely proportional to the relative radius. And here we're going to actually illustrate this fact. So this is a common electrostatics question. So we have two conducting spheres that are going to be connected by a wire and allowed to reach equilibrium. Well, it's conducting spheres. So we got the C word. No, not that one, conducting. And it says that equilibrium is established. So we know that E equals 0 inside, and we know that V equals constant at equilibrium. So we could check. They're actually not in equilibrium right now because the potentials are different. Because if we tried to do the potential, KQ over R, like K times 500 over 2R versus K times 100 over R, we would see that this sphere is at higher potential than this. Of course, my units weren't right or anything like that, but so we could prove that this wasn't in equilibrium right now. So this is actually going to tell us that charge is going to go this way. We're eventually interested in finding how much charge is going to be on each sphere. If you can instantly see this and use proportional reasoning, excellent. We're going to show the boring, raw way first before we get smart about it. So first, let's derive an equation relating the potentials of each sphere. So we know that due to them being conducting, they must have the same equilibrium potential. So this means that KQ over R for the first sphere equals KQ over R for the second sphere at equilibrium. And this is what we mean by an electric potential equation. We can do some simplifying. KQ1 over R is equal to KQ2 over 2R. And I might leave it like that just to show that this is electric potential. Yes, I understand. I can do a lot of canceling. but you might want to just simplify this already because you can see the K and the R appear on both sides, so they can cancel out. So you'd actually get the relationship Q1 is equal to Q2 over 2. Interesting. The sphere with half the radius has half the charge. So we can start to sense some linearity things coming on here. Derive an expression relating charge conservation for the system. So another thing is these spheres are connected to each other, but nothing else. So they can't change the total system charge. So what this means is that Q1 plus Q2 is constant. Can't change, because where's the charge going to go? Q1 can give charge to Q2, Q2 can give charge to Q1, but they can't change their total balance. So this means that Q1 plus Q2 have to combine to 600 microcoulombs, because there is 500 microcoulombs and 100 microcoulombs, so we have 200 microcoulombs of charge budget. If there's negatives, you could get some cancellation, of course. All right, now it's linear system time. Calculate Q1 and Q2, and then maybe see how we as smart people could have seen this value coming without dealing with systems. So our first equation reduced to Q1 equals Q2 over 2. And our second equation was Q1 plus Q2 equals 600 in units of microcoulombs. Well, you are just begging to be substituted. So I am going to replace Q1 with Q2 over 2. So then we get 3 halves Q2 is equal to 600. So then we would get Q2 is just 2/3 of 600, which would be 400 microcoulombs for Q2. And then, of course, we know these need to add to 600 by our first equation. So our missing charge is 200 microcoulombs to make that work out. And we can check that this works because we said Q1 is half of Q2. So 400, half of that is definitely 200. And then they need to sum to 600, which obviously they do. Now, another clever way of looking at this is just using the radius. So this conductor essentially is just sharing this whole charge over its whole radius. So to figure out who gets what charge, we can actually use this idea of a radius share, where Q would be equal to Q total times sort of your radius divided by the total radius of the system, which is a lot more complicated sounding than it actually is, because this is just saying, well, there's 600 microcoulombs to give around, and you hold 1 R of the total 3 R's worth of radius of the system, so that's 200 microcoulombs. And same thing over here. We have 600 microcoulombs of charge to give around, and you hold 2R out of the 3R. So you hold 2/3 of the radius. So this is 2/3 of the system radius, so it gets 2/3 of the system charge. So we'll get really clever to actually do this last problem, because 3 conducting spheres touching, ain't nobody got time for that. Is that an outdated reference? It probably is. Probably is if that was a thing when I was in high school. But the message is clear. We ain't got time for that. We don't have 3 systems of... We're not doing a triple linear system. That is a waste of our time. Even though we can do some nice symmetry things because these 2 things have the same radius. So we will be very clever, because we know that the net charge on the system is what cannot change. So this is the same scenario where we just have 3 spheres. Ooh, big deal. We have 3 spheres. The potential is still the same at each. We'll use that principle later. But Q net is constant. Or I guess not Q net, but Q total. So you have 8 Qs for the cause, you have 10 Qs for the cause, and you have -4. So 8, 10, and -4 makes 14. So I know I have 14 Q to give between all 3 of these spheres in total. And now we can use our clever reasoning skills. So what we could do is we could say KQ1 over 3R equals KQ2 over 2R equals KQ3 over 2R. And then we could set up all these linear systems. Not a good use of our time, because we said that we are clever. We know that it's exactly linear related to how much of the radius you are holding. So Q1 is equal to 14Q times its share of the radius. So I have 3r, I have 2r, and I have 2r. So that means that my effective system radius, which we probably actually want to move down a bit here, this means that our effective system radius is 3 plus 2 plus 2, which is 7 R's. Oh, that's very suspicious looking that we have a 7 and a 14. It's almost like I wrote it that way. So this means that we can just multiply by R divided by R total. So in this case, the first sphere is holding 3 of the 7 R's, so it must hold 3/7 of the system charge. So it would hold 6Q. Because 7 and 14, that divides out to 2, and 2 times 3 is 6. We could actually break out the symmetry word here and just know that since these spheres were identical, they're going to share the remaining charge, but we'll show that this works. So, same idea here. Our sphere R2, you have 2/7 of the system radius, so you must hold 2/7 of the system charge, which makes 4Q. And then lastly, we know by symmetry or by addition, this also has to be 4Q, but just to show that it works out the same way, for completeness, we'll write it out. Give myself a little more space. Apparently Q2 decided to escape from us. There you go. You also hold 2/7 of the system radius. So you would also have 4Q. And notice this works out, we know this works out multiple ways. So first, we see our fraction worked out because you have 3/7, you have 2/7, you have 2/7. What does that add to? 7/7. So we see that the 14Q is distributed. So our final answer would be you have 6Q, you have 4Q, and you have 4Q. And our last thing we should do is we can actually verify that this works, because the potential would be K times Q divided by R. So this is 2KQ over R. This potential would be K times Q over R, which is also 2KQ over R. So these two potentials match. And then obviously this potential would be the same because it's the same charge and same radius. So we actually have just proved that the solution works, because if you found a solution for potential, you know it's the solution. I believe that's a property of the Poisson equation, or Laplace's equation. If we actually go deeper into E-statics, you could prove that if you find a solution, you know it's the solution. So if you just make up stuff and the potentials work out, you actually know it's right, because all these spheres share the potential at the end. Which makes sense, because if they didn't have the same potential, charge would be transferred. All right, that's everything with algebra-based E-statics.